Hello everyone, welcome to this first module on optical transmitters. In the introductory module, I have spoken to you about the importance of optical communication systems, how optical communication systems is driving up the data rates that we witness today. It allows you to view video on demand, it allows you to send emails across continents, it allows you to share data to a wide range of people who are all spread all over the parts of the world. Now, as we saw, one of the things that has happened over the last few years is that the communication technology for optical communication has progressively become more complex. It started off with a very simple modulation technology, modulation being a process in which you take the data that needs to be transmitted, which would come in various forms, and then convert that data into optical means, so that it can be better matched to the characteristics of the optical fiber. So, we have seen that in the early generation optical communication systems, this modulation was fairly simple. All you had to do was to vary the intensity, talking about the digital communications here. So, you had to just vary the intensity of the light source, which would be either LED or a laser, although today it is lasers which are currently being used for all long haul optical communication systems. So, you take that laser power and then vary it in accordance with the modulation signal. So, if the modulation signal happens to be in the form of ones and zeros, and 1 being represented by a certain voltage level and 0 being represented by a certain voltage level, these voltage levels have to be converted into optical intensities or optical powers. The simplest of that scheme would involve sending no optical power or 0 optical pulse when a bit 0 arrives as the modulation data, and you send some amount of optical power. So, in order to represent that there is a bit 1. So, this kind of a simple on off keying, as it was called, was the hallmark of the first generation optical communication systems. They of course are still being used, but with the data rates that are clamped at about 10 to 40 Gbps, you cannot really move beyond that with these methods. So, what we have seen is that this simple method, which was hallmark of the first generation, second generation, third generation systems, are now going to be changed for the current generation and for the next generation optical communication systems. Modulation has now modulation in optical communication now means modulating both amplitude as well as phase. So, in general what we are going to do is quadrature amplitude modulation, and what we need to understand first is what different optical transmitters are available or in order to implement these complicated or complex modulation technologies. So, that is what the job of this module is. We will begin with the simplest transmitter structure, and then we will scale up the complexity as we go in order to cover quadrature amplitude modulation. So, we begin by looking at a typical and at a very high level optical communication system that would first start with a source of data. So, you need to have a source which produces data. In this module, and until we talk about it other way, we will assume that we are working with digital communication systems for all the advantages that we have listed in the first module. So, our sources are ones and zeros. Of course, these ones and zeros do not come from anywhere, they are just abstract quantities. Where do these ones and zeros come from? They are actually obtained by a process of converting an analog signal, which comes perhaps when you speak on phone or when you have some other continuously varying quantity, when that needs to be transmitted over the fiber using digital communication. The first job would be to convert this analog signal into a digital signal by very well known processes, and these digital signals are then encoded to form the appropriate digital data. So, in the simplest of the scheme, this digital conversion, analog to digital conversion, will mean taking an analog signal and converting into sequences of ones and zeros, and to represent those ones and zeros you have to choose appropriate voltage or current levels. We will talk about such mapping of bits ones and zeros, which represents the information, and their physical realization and how it would affect the communication channel. This process is known as line coding. We will talk about line coding in the next few modules, okay, after a few modules. But for now, we will simply assume that I have source, which I am labeling it as a data carrying or a data producing block, and this data that produces will be in the form of ones and zeros. So, I have a sequence of ones and zeros which would then form my data pattern. So, at any particular time, which I will denote it as n, I have a data d n which can be taken from group of ones and zeros, and it would be a sequence of this data. Okay. So, let me just rewrite this one in a slightly better way. So, I have a source which produces a sequence of data symbols which would be say 1 0 1 1 0 1, something like that at any given time. So, if you think of this as discrete time indices, at any given time n, okay, you have one data bit that is generated, which I am denoting as d n, and this d n could be either 0 or 1. This is the simplest scheme which I am assuming. Of course, this data sequence could be complex when it tries to represent more than 1 bit per symbol type of modulation. We will talk about that later. So, you have a source which is decidedly the digital communication which gives you the digital sequence, then it has to be converted into optical signal. Okay. This sequence of course has to be line coded, as I said, in order to represent the out. So, the output of the line coding block would be a sequence of voltage pulses or current pulses depending on the modulation method that we are doing. So, these ones and zeros would be represented by certain pulse shapes. Okay. These pulse shapes are of course functions of time, and these pulse shapes are the ones that will go and drive the optical modulator block. So, this would be, let us say, the voltage pulse V of t that would represent that particular sequence which we have written. Okay. So, it could be any sequence which then has to be converted into this physical voltage or a current variable. Next comes an optical transmitter. This optical transmitter will necessarily have one more input, which is a laser source. As I said, for long haul optical communications, it is a semiconductor laser that is used as the light source, and we are labeling that by this laser. We will come to some of the important characteristics of laser in a few minutes, but for now it simply provides us with an electric analog of an oscillator. So, this laser is actually an oscillator for all our purpose in this module. So, this light coming from the laser will be modulated according to the pulses. Remember, these pulses which are input to the transmitter are the outputs of the line coding block, which means that these pulses directly represent the information or the bit sequence that would be transmitted over the fiber. So, you have bits, bits are converted to pulses, pulses are in the electrical domain, voltage or current, which then has to be converted onto the optical domain by this optical transmitter. So, this process of going from electrical to optical, so the process of going from electrical signal, it need not be these pulses, of course, it can be in general any electrical signal, from electrical to optical signal, which is obtained by modulating a laser. So, this is obtained by modulating a laser, okay, is called electrical to optical conversion. So, the transmitter side is characterized by an electrical to optical conversion, so that the output of the optical transmitter will be light, and this light, as I said, could be either in the form of pulses when you are performing an on off keying or intensity modulation of the bit sequences. It could be a different kind of a signal, it could be a phase modulated sinusoidal signal when you are modulating the phase of the laser light. So, we will talk about that later. So, what you have to remember is it is light which is coming out of the optical transmitter, which then will be given to the optical fiber. Okay. So, this will then be given to the optical fiber. The fiber will carry light which is incident at its input at the fiber one end of the fiber. It will carry these light waves from one point to another point at which you locate your receiver. So, this is the transmitter block and this is the receiver block. Depending on what modulation that you have performed, you have to demodulate. Actually, you have to first detect and then demodulate. Detection means detecting the parameters of light, which most often means detecting phase or amplitude or power. So, you first have to detect by using a photo detector, then demodulate the appropriate to obtain the appropriate signal which has been the transmitted signal. You could of course do some signal processing here and then finally retrieve the data symbol. So, you finally have the data symbols which have been transmitted. Okay. So, the data sequence which was transmitted will be received at the receiver. If you look at what is happening here, you have an optical domain, but once you put in a photo detector, right, once you put in a photo detector, what you get is an electrical signal. If everything has gone well, there has been no noise in the system, then this electrical signal will just be the replica of whatever the electrical signal that was used at the transmitter side. So, if there is no noise, if the fiber has no loss, detection process is extremely ideal, nothing has gone wrong in the entire system, then whatever you have put in at the transmitter input, which in the form of the electrical signal, is what the electrical signal that you would get at the detector. Okay. So, with some non-idealities such as loss, if you include, then the electrical pulses would appear, but their amplitude would probably be lower. Actually, that is because the amplitude of the input light itself would have gotten lower because of the fiber losses. So, I hope this diagram is clear and you have identified the feature that is present at the receiver side, wherein light or light signals are converted into electrical signals. So, the receiver side is characterized by converting an optical signal into electrical signal. So, converting an optical signal into electrical signal, this one by means of detection by using a photo detector, and this is characterized in general as optical to electrical conversion. So, the transmitter can be in a very big picture way thought of as an electrical to optical converter, and the receiver can be thought of as an optical to electrical converter, with the idea that whatever you transmitted at, or the transmitted symbol Dn was there at the transmitter, would be the same symbols that you would expect, or would be the same data that you would expect at the receiver. Of course, the real world optical communication system will not mean that, it will mean that Dn is almost always not equal to Dn prime. There will be some errors. Then this system is characterized by how many errors we make in the form of what is called as a bit error rate. So, how many errors we make per second. So, this is the characteristic of most digital communication systems by giving you the bit error rate. What if the input signal, electrical signal, were to be an analog signal? Then most likely would characterize it by one of the performance measures of signal to noise ratio, or sometimes signal to distortion ratio. So, whether the signal was distorted. As I said, most long haul optical communications today, and in fact most communications today, happen by digital means. So, we will not be looking at analog modulation for quite some time. We will of course come back to analog modulation after we have looked at some of the transmitter structures. Alright, in the remaining time of the module, I will attempt to describe the transmitter to you. You have to keep this particular block diagram in mind. You start with the source, you have the data sequence which is produced by the source that needs to be converted into an electrical signal in the form of pulses. This is called as line coding or pulse shaping. From this line coded electrical signal, which you would provide as inputs to the optical transmitter, out comes the light. This light which is coming out of the transmitter would represent whatever the electrical signal that was fed to its input, and this light signals, modulated light signals, are carried away by the fiber from one point to another point, at which they are detected, demodulated. If necessary, you perform some signal processing, and then finally your data symbols or data sequence emerges, with the hope that you want to minimize this BER. So, you want to keep making the errors to be very small. So, with the objective that we need to keep the bit error rate of the system to be at its minimum. So, this is what we would like to do. So, keep this block diagram in mind as we now go to source. As I have said, optical communication systems require a laser source, because it is the laser which produces light, and that light would have to be modulated in order to carry information from one point to other point over the fiber. So, as I said, lasers is what we are using for long haul optical communications. In terms of its functional viewpoint, remember I talked about in the first class that learning optical communications, to my mind, requires three different layers to understand it completely. First, you have the functional approach or the functional layer, in which you are concerned with what is the input to this block and what is the output of the block. So, this is at a very high level without going into the details kind of a relationship. This would be characterized mathematically and graphically and by other means. We will prefer to look at it mathematically, and then if necessary we will also introduce some pictures to clarify what this functional block is doing. So, this is the functional approach. So, the functional layer. So, at the functional layer you are concerned with what is input, what is output, and what is the relationship between these two. The next layer would be to see what physical elements will realize this functional layer. So, if I have to say that give me an output which would produce a 0 for some time and produce a 1 for some time, I have to understand what physical system I have to realize in order to implement this particular functional relationship. So, that is the physical layer. So, or as I would call, that would be the where you are looking at the physics of the devices. Once you have understood the physics, and you would realize that no physical device can give you the exact functional relationship, there will be some imperfections in the physical system. The question then becomes, how do I characterize this physical system which is doing its job, but it is not doing its job very well. So, these problems that are there in the physical system, how do they affect my overall optical communication system. So, this is at the third level where we are assessing the performance of an imperfect block. So, these are the three layers in which we will proceed. So, for the source we will today look at only the functional approach. As a source, if you remember your electrical communication systems, you had a carrier. So, you had a typical electrical communication system which had a carrier, and this carrier was being modulated. So, you had a modulator block here. To this modulator block you had your data, or sometimes called as the message signal, and what you obtained was the modulated carrier. Amongst different types of carriers, we have chosen, in most electrical communication systems have chosen to communicate with sinusoidal functions, right, or sinusoidal signals. What are the characteristics of a good sinusoidal signal? Well, sinusoidal signals are characterized by three parameters: its amplitude A, its frequency omega in radians per second, this is the angular frequency. If you want to specify frequency, you are free to choose that frequency in hertz as well. I denote this frequency by omega with a subscript s, indicating that this is a signal frequency, and the corresponding source in optical communications is called as a signal laser. There is nothing specific about what a signal laser is. All it simply, there is nothing special about what a signal laser is. It is actually a laser which is used for communication, but the word signal indicates that this laser is found at the transmitter side, and it is that light which is coming out of the signal laser that gets modulated. So, that is the reason why we put this subscript s. So, if we see, it has amplitude A. Equivalently, you can characterize this one by a power P. Normally, you do not do this, but in optical communications, power is a main thing that you can, power is the only thing that you can actually measure. You cannot measure the amplitude of a light wave. Therefore, power becomes the fundamental component in optical communication system. So, we do represent that one, and again to distinguish that this is a power of the signal laser, we put a subscript Ps, okay. And amplitude and power are normally related by this relationship, that is square root of Ps. So, amplitude is related as square root of Ps, okay. So, this is a typical relationship between amplitude and power. So, when you square the amplitude, you get the power. So, this squaring is kind of a normalized amplitude square, which will then give you the power in the system. So, there might be some constant sitting in, we do not really bother about that one pretty much. The third parameter that is important for phase modulated optical systems, phase modulated communication systems is the phase. Of course, in a sinusoidal signal, this phase would be with respect to a certain reference signal, right. So, you can take either a sinusoidal signal as your reference, or you can take a cosine wave as your reference. Normally, we take the cos signal as our reference and say this other signal sine is 90 degrees lagging by this cosine waveform. So, remember these waveforms actually extend all the way to minus infinity to plus infinity. So, if you call this as signal S1 and S1 of t, and this one as your signal S2 of t, then we say that S1 of t is also a sinusoidal signal, but it has a phase of minus 90 degrees. It is lagging by this particular signal S2 of t. So, that is what the relationship between a sine and a cosine wave is. We actually perform what is called as quadrature carrier multiplexing, in the sense that we put data onto the cosine part of the signal as well as onto the sine part and combine them. Both have to be at the same frequency. This quadrature carrying multiplexing is also known as IQ modulation. We will talk about IQ modulation shortly. So, coming back to what we want from a sinusoidal carrier, a sinusoidal carrier has well defined power or equivalently amplitude. It has a well defined single frequency omega s, and then it has a certain phase which would not become important unless you modulate the phase. This is at the functional level where I am looking at. So, I have a carrier, okay, and what the carrier does is to produce a signal which, let us call it as S of t, okay, given by square root Ps. Remember, amplitude and square root of Ps are related, cos omega st plus phi, where phi is any phase with respect to cos omega st. So, this is the functional relationship, or this is the output of the carrier. Of course, it does not take input in the functional form. So, there is no input to the carrier, but a physical laser will take input in the form of the current that you need to provide in order to bias the laser. So, this is the output in the functional viewpoint mathematical expression which characterizes my carrier. This, remember, if you have noticed here, the carrier description does not say whether this waveform is described in the optical domain or it is described in the electrical domain, because the characterization of a functional viewpoint is the same regardless of whether you are in the electrical domain or you are in the optical domain. Okay. So, this could very well represent an electrical sinusoidal signal. It could also represent a nice light, optical signal of frequency omega s. The difference being, the frequency omega s is usually very large for optical signals. It is in the order of terahertz, whereas for electrical signals you normally go up to gigahertz. So, this is typically the optical frequencies. Gigahertz is normally how much you can push it to electrical signals. Okay. And this phase, as I said, unless you modulate, it normally does not enter into picture. For intensity modulation systems, this phase is totally immaterial. Intensity modulation or the on off keying signals, this phase is totally immaterial. Now, this description which I have given is a description in terms of time domain relationship. If you remember your signals and systems, it is possible to go to the frequency domain and describe what you are getting as the output of the carrier. So, how do I describe the carrier in the frequency domain? Well, what I do is I consider the frequency axis, so call this as axis omega, and then take the Fourier transform of the signal S of t. I can do that because this is a nice sinusoidal signal. Stepping aside any mathematical difficulties that could be perhaps arising because of this type of a function, you have probably seen this one. The description of a sinusoidal signal would be to give its Fourier transform, in the Fourier transform, to denote it by two delta functions. Here you have two delta functions which are situated at the signal frequency omega s and minus omega s. Remember, this is a real signal, so it will have its spectrum which is two sided spectrum. Okay. There are certain amplitudes to this. So, this amplitude is square root of Ps divided by 2. It is the same amplitude for both sides, and there is a relationship for the phase as well. So, if you look at in terms of the frequency omega again, and if you were to look at the frequency of, if you look at the phase of the Fourier transform of S of t, let us call the Fourier transform of S of t as S omega. So, this would represent the magnitude of S of omega, and if you now look at for the phase of S of omega, you would see that this one has a phase of phi and this one has a phase of minus phi. Okay. So, I guess that this is all right, because you can write cos omega st plus phi as e to the power j omega st plus phi plus e to the power minus j omega st plus phi. And then if I take the Fourier transform of this would be a delta function located at omega s, this would be a delta function located at minus omega s, and this would be the phase relationship. You can switch the phase relationship calling this as minus phi and this as plus phi, but they have to be antisymmetric with respect to each other, whereas their magnitudes are symmetric with respect to 0 frequency. So, this is the 0 frequency. So, this characterization of a carrier, it applies equally well to a electrical signal or it will apply very well to a optical signal, describes both in the time domain as well as in the frequency domain. Now, we in our optical communication systems, this carrier is nothing but a signal or light generated by a laser. So, this is the light that is generated by a laser. We will assume that this laser is well behaved in the sense that it is characterized by certain power Ps, which is typically in milliwatt region for optical communication systems, 1 to 10 milliwatt or 1 to 20 milliwatt depending on the lengths that you require. It is also characterized by its frequency omega s, which as I said would be in some terahertz, or rather the corresponding frequency fs will be in terahertz, okay. And this is also characterized by a certain phase phi, okay. This is a single frequency optical signal. You will later see that there is no such thing as an ideal laser, and a laser typically has a spectrum which looks like this. It has a spectrum. I am just showing one half of the spectrum here, which is located at omega s. What you would see is that the spectrum is actually a broad skirt around the central frequency or the signal frequency omega s, and this broadness is characterized by the line width of the laser. The laser has a non-zero line width. So, in the popular language or in the popular thinking, laser means it has a single wavelength and it has the spread around that particular single wavelength or the wavelength of the laser, but in practice no single wavelength or a single frequency laser can be obtained, and most lasers have some amount of line width which is measured typically in some megahertz. So, these days you will get very good lasers which have a few megahertz line width. So, this line width typically is around anywhere from 100 kilohertz to 1 megahertz. Okay. We will see what is the implication of having the line width later on. Also, the power of a light wave that is generated from the laser will not be constant, but it would actually be fluctuating. Okay. So, this delta p of t represents the random fluctuation. So, you would expect that the laser to have a constant power, but it does not really have a constant power. It has a power which is average power is Ps. Around that there would be fluctuations. You can see that fluctuations, assuming that you have an ideal photodetector. You take a laser and then take a photodetector. If your photodetector was ideal, producing no noise, then if you give laser, set its power output to some Ps milliwatt, what you would expect is this characteristic. So, if you look at it as a function of time, you would expect the power to be constant and has a value of Ps. However, if you actually look at the measurement, the real data shows that there is an average power, okay, and around that average power there are these fluctuations. So, you could characterize the power of the laser as not being a constant, but rather changing with time, and this time changing has two components. It has an average value, okay. So, it has an average value Ps and it has a fluctuations delta p of t. So, the fluctuations are obtained by subtracting this green line from the red line, okay. So, when you subtract that green line from the red line, what will happen? The red has 0 average value because it has been subtracted, the green has been subtracted. So, this would be the fluctuations that you would see. So, this is the fluctuations delta p of t that you would see as a function of time. This completes our functional description of the laser. At this point, we will see the imperfections of delta p of t, which is there in the physical system, as well as the line width. We will see what physical mechanisms are responsible for this line width as well as these fluctuations in the power, and how would they affect the optical communication system, how would they affect the performance of an optical communication system as we go along with the course.